So this lecture is really understanding the acid shortlist more than anything else. So the shortlist of acids is really what I want you to take away from this. But in order to get you in the right mindset, I really want to talk first about what Prof. Pka calls first principles and Professor Miller calls ROEs. Resonance, orbitals, sterics, electronics. This, I think, is the best lecture to introduce these concepts to you because everything in the acid shortlist that we're going to talk about really stems from these principles, the first principles from ROEs. And if you understand what's going on, then the shortlist becomes really easy to memorize. And more importantly, once you have the shortlist memorized, then you can extrapolate to other things. So that's really why I wanted to. So where I want to begin is in illustrating that the shortlist really should be laid out as though you're on the periodic table, and then we can fill these in any order. But let's start with electronics, the bottom of this ROEs thing. We're actually going to go in reverse order here. We're going to start with electronics, then go to size, then orbitals, then resonance. And we're going to save resonance for last because I think it's the most important, and I really want to end that. But electronics, the atom in question to which the proton is bound, will have an enormous effect on the pKa. We know that fluorine is much more electronegative than oxygen. Oxygen's more electronegative than nitrogen. Nitrogen's more electronegative than carbon. So which one of these would better tolerate having a minus on? Well, you would think fluorine, and you'd be right. The pKa for HF is 3. That's actually a weak acid. Anything that's weaker than H3O plus is a weak acid. But anyhow, HF, 3, weak acid, but still starting to be fairly acidic. Whereas water has a pKa, and we'll just round here, we'll call it 16. NH3 has a pKa that we will round to 35. Keep in mind, this is for NH3 going to NH2 minus, as opposed to NH3 picking up a proton. NH3 going to NH2 minus is hard to do. Nitrogen does not want to be minus. It is a pKa of 35. CH4, carbon really does not want to have a minus. So for all intents and purposes, this is the top of the pKa scale. 50, you won't do it. 10 to the 50th. No molecules want to exist as carbon minus. This 15 gap is 10 to the 15th. It's an absolutely enormous gap. And then from nitrogen to oxygen, we have an even bigger gap. This is 10 to the 19th. This is enormous. Okay, so electronegativity of the atom in question matters quite a bit. You can't, for any intents and purposes, put a minus on a carbon. Therefore, the pKa establishes the top end of the scale. Methane, pKa of 50 is about as bad as you're going to do. Ammonia is not great, pKa of 35. It's a very weak acid, meaning that NH2 minus would be a fairly strong base. Relatively hard to pull off a proton from NH3 to go to NH2 minus. That's what that means. Water does not particularly want to give up that proton in order to become OH minus, 10 to the 16. HF, far more willing than water to give up that proton. Okay, that's the trend for the electronics. For size, we now have a very dramatic trend. Taking off the proton from fluorine is relatively hard to do, but HCl is one of the strong acids. Its pKa is -7. pKa for HBr, depending on which handout you're looking at, is around -8 or -9. It's relatively easy to take off this proton. In fact, it's 100 to 1,000 times easier to take off the proton from bromine than it is from chlorine. And HI, of course, being the biggest of the counterions, is even stronger as an acid. So if you look at this trend here, what we have is size clearly makes an enormous difference. Go from a weak acid to a strong acid, going from fluorine to chlorine, and then it gets better as you get bigger. So, question then, if water has a pKa of 16, what would you assume would be the answer for hydrogen sulfide? And the answer had better be that the increased size of the orbital matters. And sure enough, it does. For rounded purposes, I have stored away that a thiol has a pKa of around 10 rather than 16. Said another way, it's 1,000,000 times more potent as an acid. It is willing to give up that proton about 1,000,000 times more than water. So we've now covered the electronics and the size components of ROEs. What we have left is orbitals. So imagining again that we have methane, a double bonded structure and a triple bonded structure, then let me just simply write down what those values are. Attempting to remove a proton from methane is again very difficult to do, 10 to the 50th. Attempting to remove a proton from a double bonded carbon, an sp2 hybridized carbon, is still very hard to do, pKa of around 45. Attempting to remove that same proton from this one is dramatically easier, 10 to the 25th times easier than doing it with an sp3 hybridized carbon. I'm hinting at what matters here, the orbitals. In this case, we have an sp3 hybridized carbon, which means that the s orbital makes up about a quarter of the hybrid orbital that the hydrogen is bonding with. In the next case, we have an sp2 hybridized CH bond, and the s orbital makes up about a third. In the bottom case, the s orbital makes up about half of the hybrid orbital, making the bond between the carbon and the hydrogen. The reason why this matters is because the s orbital is close to the nucleus. Said another way, the minus charge that results when we pull off this hydrogen is held closer to the nucleus in this case than it is in this case, and that significantly changes the acidity of the proton. It is 10 to the 25th times easier to pull off the proton from an sp hybridized carbon atom than an sp3 hybridized carbon atom. So let's review. We talked about electronics. The electronegativity of the atom that the hydrogen is bound to is crucial for the purposes of acidity. We're scanning the difference from a pKa of 50 to a pKa of 3. 10 to the 47th. Sterics plays a very significant role as well, going from 10 to the minus 3 to 10 to the 10th. So about 13 orders of magnitude. 47 orders of magnitude with the electronics. 13 orders of magnitude based on size. Here we have 25 orders of magnitude, orbitals. These are clearly very important things to keep in mind. And yet, I wanted to finish with resonance because I think resonance is one of the more important values to keep in mind as we move on in the course. For the purposes of remembering acidity trend, electronics is biggest effect. But for the rest of the course, resonance really has a very important contribution to play for remembering trend. So these are ordered in no particular order other than resonance I consider to be more important than the rest. But when it comes to acidity, resonance is relatively less important than some of these other effects. For example, we have here a alcohol. What is the pKa of an alcohol? Well, to a first approximation, alcohol is the same as water. So the pKa for an alcohol should be about 16. pKa of a carboxylic acid, I want you to just remember as 5. So if we can take a minus charge that would otherwise be localized on this atom, and we can smear it around in space, what we have is now two good resonance structures where the minus is shared equally on the two oxygen atoms. What's that worth? Well, that's worth about 10 to the 11. It's a very significant effect. By the same token, what is the generic pKa for an alcohol? It doesn't matter what the alcohol is, you would do well to remember 16 as a first approximate. However, if you have a resonance stabilized alcohol of this type called a phenol, then this has got a pKa of about 10. Why is this so much worse? Well, even though you have lots and lots of resonance structures, all of the resonance structures that I'm going to draw, other than the first, put a minus on the carbon atoms, which isn't as good. So having the ability to spread the minus across two oxygens is worth about 10 to the 11th in this case. Having the ability to spread the minus from an oxygen to a carbon is worth about a millionfold, 10 to the 6th. It's nowhere near as good. It's still good, but nowhere near as good. The final resonance example to include is a pretty important one because it shows how big an effect this can be. But if I have a propane, then the first approximation pKa for that would be about 50. But if I have a nearby ketone, then the first approximation for this is about 25. The pKa of this is going to be about 25 because the minus that results when you deprotonate can now be shared onto a nearby oxygen, and this particular resonance structure dramatically stabilizes. This is worth about 10 to the 25th pK units, which is again a very significant effect. So what are the first principles I want you to remember? Really, rows: resonance, orbitals, steric, electronics. For the purposes of acidity trends in general, the relative rank ordering of rows is not as strong. Electronics is probably the largest single effects, and sterics is well worth keeping track of, which is to say the size of the atom that will need to stabilize the charge when all is said and done. However, when you move on to other problems in the course, resonance is something that's easily overlooked, and so I would say that you should always have resonance in the front of your mind when you're considering the first principles problem. It is the one that you're most likely to forget about, therefore it's the one you need to think about first and analyze in order to see how it affects the system in question. So, use the acidity chart, the short list, to help you remember these trends, but also use these trends to help you remember the acidity chart, to remember the short list. And then use the short list to help extrapolate. You can, based on these trends observed here in size, then make predictions about how sulfur relates to oxygen, how phosphorus relates to nitrogen, and so on and so forth. That's the utility of the short list. That's the utility of the first principles, especially as enumerated in rows.